All right. Hello, Henrik.
Hey.
Chris, Nico, and Colin. How are we all doing? Henrik, what's new?
I've just joined the master class on the CatCat Edu. And actually, you know, it has the same installation problem, the master class, as the bootcamp did with this requirements. But it actually worked with, except the requirements are just huge on this master class. So I changed it to import again, which actually works, but it takes 10 minutes. So I don't know if you want to maybe put a comment into the script there. So if you're a Windows user, perhaps use this one, and it's going to take 10 minutes to load. Kind of, I don't know, because I was like, what's going on? Is it crashing? But it didn't. It just took a while.
Interesting. That's so weird that the issue keeps coming back.
Well, as I'm not the only one, I guess it's not just me.
Yeah. No, there have been multiple people running into that.
I'll put a note in the comments section so people opening it get frustrated.
Yeah. Nice. The class looks really exciting though. Well done. Pretty thorough. I think they've been working on it for a while, so it's cool to see that get released. And hello, Joes and Lawrence. Thanks for joining.
Hello, everyone.
Okay. Chris, I hear it's been a party in Vienna this week.
Apparently, yeah, but if there was a party, I haven't been invited.
Your daughter was invited.
This is true. Yeah.
Adorable, gorgeous baby girl.
No, it's a great event. It's great. It's a pleasure having guests here from all around the world visiting to Vienna. It's a great experience. Yeah.
It's a research party.
True.
Just as fun. Okay, we can give it maybe another minute. Hi, Paulina. Welcome.
Hi, everyone. Thanks.
Okay. I think that is enough cushion for now. I will continue to let folks in as they trickle in, of course, but suppose we can just get started. I actually don't have any updates on our end. This is lecture number 6, week 7, lecture 6 of the program so far. So we're we've made good headway. I think learned a lot. Have had a bunch of awesome discussions. Hack and share session last Tuesday I heard went well. Even continued for a few hours offline in the Discord voice channel. So very cool to see that. And yeah, I think we can just jump on in for today. Jamshid or Barlin, I actually don't know which one of you is starting, but I'll hand it right on over.
All right, thanks very much. I will get started here. I'm going to jump in on the tablet, so I apologize for the video dropping out as I switch windows here, but hopefully this will screen share correctly. So let's see here. Okay, can everybody see my screen? Can everybody see the slides?
Yep.
Excellent, great, that worked. Okay, so we're in week 7, lecture 6, session 5 of our first of these 6 kind of intro lectures on the engineering design process as applied to the OMNIPool from HydraDX. Today we're looking essentially at the movement from the blueprint that was created from the math spec into one of many potentially, but one which actually is well suited for the framework to implement the blueprint in CatCat. And some of you, of course, all of you have had some experience already with this. We've been using it as a vehicle for demonstrating different aspects within the GDS and the math spec until now. So now we're going to kind of get into a little bit of proselytization in a sense as to why it is that CADCAD, among other alternatives, is a nice implementation to be looking at, but also to kind of dig into a little bit more detail, and again, reinforce some of the mappings that we've been calling back into for things like requirements and how they are being translated, first into mathematics, then into a representation of that mathematics into a formalization in a computer environment. So what we'll do is begin sort of with a what is CatCat introduction, which provides a little bit of the motivation and also takes a peek into different aspects of using CatCat even beyond what we will be doing next week. Next week, we'll be looking at how you can select between alternative mechanisms by running experiments. And then there's a little bit of things that you can do once you confront the CatCat environment to real data. So we'll give a little bit of just a brief touch on that. We'll then go through the reference implementation of CatCat itself, which will be partly a codification of what you have already seen before, but essentially brought up into its specification as a computer implementation of the Hydra OMNIPool. So we'll look at that in detail. Then move into the execution of the system, the live execution of the CatCat environment, and how the Hydra AM is put into that framework, and finish out with an assignment on the basis of an extension of that reference implementation work and own work that Chris has put together in the form of kind of a catch-all tutorial or a how-to guide for CatCat. And so leveraging that documentation that is hyperlinked in this presentation, but will also be, I believe Chris will be placing it in the channel, to be able to use that also to figure out ways in which you take your own system of interest and understand how to move through the math spec into the implementation of CatCat. So just to begin with what you, in a sense, have already seen and maybe have already intuited, what CatCat is. Now, it stands for Complex Adaptive Dynamics Computer-Aided Design. And from that mouthful, I would highlight the complexity. These are systems, as we've seen, from generalized dynamical systems that can be very abstract, and also computer-aided, so that it is not something which exists in a vacuum from the researcher or from the practitioner who is attempting to tease out regularities or system properties or requirements. It really is a method of understanding how to assist in that framework that is created all the way from the stakeholder desires and the different types of goals that people have to operationalize the questions that can be answered and put them into a framework that a computer can assist in that answering by leveraging the ability of a computer to do things that would take many person hours otherwise. The framework itself is CatCat, as you know, is an open source framework. It is essentially built around the notion of implementing a generalized dynamical system. And for running experiments and simulations, within that classification of different mechanisms that are designed to reinforce certain system goals within that generalized dynamical system framework. It can be run specifically and is, as its reference implementation is classified as something running in Python, but part of BlockScience's current work is to start to make it more performant by using alternative languages such as Julia, and you can, in fact, port it to other languages. That's something, of course, is an open source framework anybody can do to see if there are performance improvements that can be done within that context. The thing that I would like to highlight, of course, is not just that it structures things according to how a GDS takes a dynamical system and moves the state from one time step to the next with the possibility of internal and external effects changing or mutating that state. It also allows one to be able to adapt different modeling paradigms to add in and to extend the existing GDS when you want to be able to refine the assumptions that you're making about, for example, individual behavior or where the data comes from, or these types of refinements that are going to affect potentially the way in which the requirements are or are not, depending on the outcome of the experiment, being fulfilled. And so these kinds of nestings or extensions that work within the same environment are facilitated through that pass-through that is extremely important, as we've seen from last week's session, that mathematical specification, both the concept math spec, which is providing the input and output, the domain and range, so everything is internally consistent with what you've seen from a GDS, and then the preliminary math spec, which says, conditional upon this type of arrangement that we need to have, what is the mechanism that we are actually attempting to implement that satisfies certain system goals or certain requirements. And we're going to talk a little bit more about what it means to satisfy system goals and satisfy requirements when we come to the parameter selection process, because one particular way to do this that leverages an environment like CatCat is to parameterize mechanisms and then vary the underlying parameters, which actually generates for you, if you think about the parameterized mechanisms as a class, it allows you to cycle through instances of the class. So different parameter values are different instances of the mechanisms that are parameterized. Now, why specifically CatCat as a reference implementation as opposed to alternatives? One reason is that it fills a gap. There is this gap that exists between open source modeling and simulation frameworks for generalized dynamical systems that do not rely upon a specific modeling paradigm. And in addition, it fills a gap between existing open source and proprietary frameworks that do provide such a generalized environment with regard to the integration with other data science frameworks and libraries that are readily available. So by comparison, there are other tools that can do things that are very similar to what CatCat does. It's just that the movement, the step that you take between the GDS framework through a math spec into an implementation is a little bit further when you're using a tool like Simulink or Stella, open source framework like Modelica. They all have their own distinguished lexicon or syntax for working with their particular implementation of a system, and then the optimization built upon that. But the step that it takes from a GDS framework implementation is smaller. That step is smaller when you are leveraging an open source framework that has a lot of fluency already existing in a community of individuals who are working on similar problems. As mentioned, we also have the extensibility of this entire system to be able to build in different types of behavior, for example, different types of exogenous impacts on the system. And that extensibility, that modularity is something that I'll highlight again. It's not to say that it is not possible to use other frameworks. Quite the contrary, it's more that there is a lower barrier to, perhaps to barrier to adoption. And just to give an idea of, in a nutshell, this slide is giving on the one side, on the left-hand side, the understanding, which is that HackMD document that I passed on the channel a few weeks ago, that this is a formal specification of a generalized dynamical system. So viewed through that lens, the transition is fairly shallow, is very low. The cost is fairly low. And on the right-hand side, there is this potentially a gradient that one might see between individuals who are trained in an environment which utilizes a proprietary technology, in this example as MATLAB, but once they lose access, having perhaps left school, which has been paying for the license from MATLAB into their own practice or into another environment, they actually then have a hill to climb to use other types of resources that are readily available in the open source community, such as scientific Python or other open source models. And so in order to well, on the one hand, you actually have the ability to help people move in that gradient by having an environment like CatCat available. But on the other hand, in a sense, it begs the question of if it can, for this particular use case in the GDS framework, perform in the same fashion as, or to provide the same functionality as a MATLAB or other proprietary environment at a cost which is significantly less, both in resources and also in time to acquire, then those stand as ready arguments for its adoption. And I've put some links here as well. Actually, I think others have put some links here with regard to where you can find some of the further introductions of CatCat as it was released into the open source, as well as the link to that HackMD for the formal specification.
And there's actually one question in the chat. Joe's,
sure.
Would you like to jump in? Joe's, would you like to jump in? Otherwise, I can.
Yeah, okay. Can it be claimed that CatCat is the only, modeling tool now existing designed to straddle both the area of A, complexity, and B, the deterministic areas?
It is probably too strong to say that it is the only. And the reason that I mention it is because it is essentially built upon regular computing environments. And so you can find other computing environments that will do the same kind of thing. Of course, Simulink is perhaps the most popular from an engineering point of view, being able to model the same environments as this. So it's not something which is unique to CatCat itself. What it is a way to leverage the structure of a GDS in the most immediate way possible. So there are fewer ways in which the system has to be wrangled, so to speak, or the way in which states are updated is a very clear pathway to building both internal decision-making impacts of how agents are making decisions in a deterministic setting or in a feedback setting, but also to allow ports or interfaces to those impacts which are coming from the outside, such as a price oracle or other noise or arbitrage opportunities for an AMM, for example. So it isn't that it's the answer. It is simply one of the answers from which a GDS math spec generation is able to be leveraged in a very powerful fashion.
If so, then can it be claimed that GDS is the best way to tackle complexity in a modeling framework?
That's a good question. So I would say that GDS is a point of view to understand how systems change over time. There are other ways in which one can think about the evolution of systems. The reason that GDS has a power, and this of course leverages both the idea of looking at this from the data science point of view, but also from the stakeholder point of view, as in I would like to engineer a system, is that it makes extremely clear the way in which the system as defined, and remember we went through at the very beginning looking at how systems are defined, what their interfaces are, what their boundaries are. So taking that as given, it makes it very clear to understand the impact of things coming from the outside versus things that are moving on the inside. And so it is a way in which an extremely general, up to the level of looking at how sets of things change over time, or how the shape of things, of the topology, changes over time. For example, how a network might grow over time. GDS is one way in which you can make that extremely precise. But again, because what we're looking at is modeling ultimately things that can be placed in a computer environment, there are things that perhaps maybe in the future would become easier to model an environment. For example, for quantum computing, there may be an entirely different paradigm for understanding how different possible path trajectories could collapse into a single one, or perhaps a way in which you could do with one operation something that would take sequentially many thousands of operations today. And that might change, in fact, how we would look at the different mathematical models that we would be using to generate something that would be reflective of the complex environment that we're attempting to model today. So I kind of built a straw man there. In the future, there might be something which is even better, simply because I believe that GDS has a very good current footprint in understanding how to apply a complex system into this environment. But I wouldn't say that it is the only way, and in the future, certainly there may be better.
Thank you.
Sure. Okay, we can think about the CatCat environment as something which is taking a GDS framework and placing it on a computer. That's one way to look at this, but what one is actually doing is attempting to solve a problem or to answer one or more questions. And so the next few slides are really to kind of just give some feeling to what it means to be able to use CatCat in an environment that allows one to understand mechanism design, or allows one to build, for example, an AMM that performs in a certain way. So on the upper side of this slide, you see a level of technical skill sets that are leveraged when moving into an environment that has real data, that has data that is available, that people have been looking at, either from prior experience or from alternative mechanisms than the one that they are creating. They're saying, I would like to build a better mousetrap. Let me go ahead and look at the existing mousetraps, for example, on the one side. And on the other side, you actually have the skills that build the business requirements or build the understanding of how to implement those business requirements as system goals, as requirements into the model, so that when you are actually taking it and confronting it with a CADCAD framework, and then taking this framework and either creating numerical simulations or taking it and confronting it with real data, you're actually doing that computer-aided design part of the system. You're looking at the system and saying, what is the data telling me about the performance of the system relative to alternative mechanisms, or even within a single class of mechanisms, alternative parameterizations, which is what we'll be discussing in next week's session. And this allows an extension of CADCAD beyond merely the selection of a particular mechanism or class of mechanisms. It also allows individuals to take the model that CADCAD is providing and use it in confrontation with their actual system that they are looking at. So that once a system has gone live, it is not that CADCAD is simply mothballed and placed into the equivalent of a computational drawer somewhere and forgotten. Rather, it can be run side by side with an actual system, taking actual data that has come out from that system, and continuously test and try to understand exactly what it is that is happening in the real world on the basis of the things that you can actually adjust within the CADCAD environment. So on the right-hand side of this diagram, you see this, there are two loops that are here. The right loop is called the pilot's loop, or the steering loop. This is actually human beings who are using CADCAD in an environment as if it were replicating or attempting to replicate the behavior of an actual system. And in that loop, as individuals make decisions on the basis of what is happening, we have what is called a digital twin. So there's a larger section of the usage of CADCAD once a system has gone live to understand both the strengths and the weaknesses of the system that are being discovered as a part of the system's running. And so this then gives a feedback, and you can see this in the yellow arrow, into a location where on the left-hand side, the left loop, the engineer, the individual who is looking at the system and the system's requirements and coding that implementation in MATLAB, starts to understand that if a signal from the pilot's loop, from the computational steering of the digital twin, indicates that something may be off, or that underlying assumptions have been changed. Or even if the organization has decided on a governance action that changes one or more structures within the system, that the engineer is then able to then go back, look at the math spec, even go back to the GDS level and see whether or not there are adjustments that are required within the CADCAD environment to make sure that it is commensurate with what is being observed in the real world. And this is a nice way in which CADCAD is able to continue to inform what is happening with an active live system after launch. So it is not simply to build the bridge and then leave the system so that the real bridge is simply running, but it's actually to take and monitor what is happening with the bridge and then go back to the model and see if it's improved or what can be changed or what extensibility has occurred. Okay. Now, the strength of CADCAD as an implementation framework, once again, just to drive home that notion that we are thinking about this through the lens of the GDS formalism. Well, one of the things that when we went through and described how GDS operates was to highlight the notion that GDS is more or less agnostic to the type of implementation of time that you as the modeler or as the individual is assuming or hoping or thinking that data will be arriving or that states will be updating as and through. So that continuous time approximations, discrete time approximations, block time or event time are all things that allow behaviors to be attributed to different time frequencies and at different levels of scale within the same environment. And so once again, this allows this mixing of different types of modeling at different time scales and at different spatial scales that gives multi-level or multi-scale modeling as an advantage to use in CADCAD. And I'll show a couple of examples of this in a moment. Integrability, of course, is something that I've mentioned already before, this notion that you have a modular formalism in CADCAD. It's modular by design, and hence it's extensible by design. That allows you to use these different modeling paradigms in a consistent fashion. And multi-scale modeling is something that is extremely important and has been well and long and well understood in the natural sciences for many, many years. It has been understood and recognized in the social sciences, but not as easily implemented. In particular, for many years in the social sciences, there was a sharp distinction between the micro level, the individual behavior modeling, and then the modeling of aggregates, the macro level, with very little in between, other than perhaps the theory of the firm, the company, as a collection of individuals operating as for example, a team. And that's changed with the ability to see more from the data that we've been able to collect over the last 20 years or so. So as a comparison, let's see if my slide deck is working. Here we go. As a comparison in the natural sciences, we have a way in which we can understand both the physical universe and also its aggregations as belonging to very small to very large and from very slow to very fast. And so here we have just an example of some of the multi-scale modeling that can be done as an evocative way of thinking about how CADCAD can do the same kinds of things, the same kinds of distinctions that exist both on the time scale and on the distance scale or the distance metric. This is one example for those of you who already have, I think many of you in the audience already have a very hard science background, but even if not, you can see that there are different axes or different dimensions under which we can examine the same global phenomenon, the brain, for example, on the left-hand side, from different lenses. And essentially, that's what's happening in a multi-scale model, is that these different lenses are allowed to interact with each other. Now, in CatCat allows the same type of thing. You're actually able to do multiple levels of interaction along the same lines. And here are 3 different examples with the links at the bottom for future looking. One of them was one of our researchers was able to look at a model for infectious disease, for infectious transmission of COVID at the time. And there are different types of interactions that are occurring at different times of day or across different spatial scales. The center one is about is a staking model. I think this is from Gitcoin, if I'm not mistaken. And the right-hand side is a tutorial demo on predator-prey models, showing different realizations using different initial conditions for exogenous randomness. And so there is, in the same way that we see has long been known in natural sciences, the ability to confer upon a GDS framework where if you're looking at the GDS and you're saying, man, I've got different types of interactions at different time scales, or I've got a network and I have different interactions across that network, across the breadth or the depth of that network. Well, the way in which the reference implementation operates is that it allows you to be able to address each of those differences, those different scales, in a consistent fashion. And so we'll see in a moment how the reference implementation allows this. Okay, and finally, it's useful to think about CatCat not just as a way of building a GDS model or of figuring out how to look at a dynamical system, but also as a way in which something that has that whole framework behind it can be implemented in a computer environment. And so you can, in fact, boil down, if you want to look at it this way, CatCat into two core elements: its semantics and its executors. And from a semantic side, that's really the programming language specific. So there are things that are built up from primitives that are then used within the CatCat environment to be able to make things easier than having to write things out very long over time. It essentially builds the modeling language within it. And then executors are the functions that themselves are able to, in a sense, leverage the way that the semantics have defined the dynamical system to be able to then answer questions about the dynamical system through things like parameter selection, through things like Monte Carlo simulations of exogenous randomness. And so building upon that, that's sort of the substrate of what every CatCat implementation has. On top of that, you could then start to say, well, what are the tools or the ways in which I would like to answer my questions? And so some of the ways in which toolkits have been built on top, some of these are also almost natively built into the implementation itself, include things like A/B parameter and model testing, where you essentially are looking at different values of underlying parameters or different models of, say, agent behavior, and then comparing them against the same system goal to see, is there a ranking that can be induced from the alternative runs that you are seeing that says that one parameter is itself performing better according to that system goal, according to that metric, than another. And as you continue to expand that, you might think, well, okay, we do that maybe for one parameter, for one particular realization, perhaps of an external uncertainty. But what happens if we just figure out or assume or get from data some kind of a distribution or a distributional assumption about that external randomness? Well, it stands to reason that drawing from that distribution repeatedly and then performing that parameter assessment would build a distribution of outcomes that may occur. And that's the heart of the Monte Carlo runs that are also a part of the CatCat implementation. And this allows then, as you move into larger and larger collections of parameters that you care about, in fact, not just parameters within the system, but even initial conditions that are set for the system, having different sets of initial conditions and then letting the system run, that allows you to build functionality around it in the way of experiment wrappers. And I'll touch base on just a couple of them. We're not going to use them in this section of the course, but they are available in the repo, the CatCat repo that you have access to. In addition to having execution hooks for things that you can plug into for things like, for example, post-processing of data and data storage if you want to store things at a high level. Okay. Before moving into the reference implementation itself, I just wanted to open the floor to any questions about what you just seen. No questions? All right, very good. Continue. So the heart of the reference implementation is as we've been describing over the last few lectures, is the partial state update. The partial state update, remember, is the way in which we are able to ensure that we're taking a particular summarization of the system as a state and allowing the things that impact that state to do so in a consistent fashion along the lines of what we're assuming this dynamical system is doing from our GDS framework. And building that particular schematic into the math spec, we are able then to understand how that update process can occur through what are called within the CatCat implementation policies. And these are driving the updates or the state transitions that occur. So on the right-hand side, you see within the purple box, you see the blue state variables, of which there can be many, each of which can impact a particular policy, which is telling what will happen conditional upon a state. There may be more than one. They may be added together. They may have other operations that impact each other. And then they each then have an impact on how the state itself is updated. That's in yellow. Once the state update has occurred, the next version of the state occurs and then the system moves forward within this one particular application that we see in the partial state.
And Jose, I see you raise your hand. Do you want to jump in with a question?
I'd like to ask, why is it called a partial update? Is it because it's being done in stages, or is it?
That's a good question. So that's exactly the next this slide. So perfect timing of your question. So the way in which the code executes, it parallelizes what it can, but it executes in a sequential fashion by grouping the different actions and mechanisms themselves according to the formalism. And the reason that this is important is that you have things that may be in the GDS simply all updated from time t to t+1, that it is actually a lot better for you as the developer or as the individual eventually implementing in the system, an actual system, to break apart as a series of substeps that each of which is executed in sequence, but when taken together comprise that single step from t to t+1. And that division, that grouping into smaller pieces, each of those pieces is called a substep. And so the partial state update block is updating, instead of the one monolithic t to t+1 change, it's breaking it into those pieces, each of which is a partial update of the state. In this right-hand diagram, you see that the purple boxes are each partial state updates, where we have individual subsets of the states being updated according to the policies, while the larger pink box with the upper left-hand side moniker of time step is the full state change from t to t+1.
So, yeah. Does it consider parallel events, events in parallel?
Sorry, I missed that last part.
No. Does the modeling consider in parallel also instead of sequential?
The model itself is written so that the individual steps occur according to a logical grouping in sequence. However, within each of these, if you have a vector and you're using vectorization, there's a parallelization that can occur. To the best of my understanding, and of course, Brian can jump in as the resident expert, it's not the case that you parallelize the partial updates in sequence, but within each partial state update block for the substep, there can be parallelization. I hope that's correct, Brian.
My question arises because if you're creating digital twins in certain high frequency situations, there might be a need for actually things to happen in parallel if reality is to be simulated.
I think that's true. There's definitely a performance question. One of the reasons why there's a lot of extant research on implementing the CatCat formalism in different programming languages, such as Julia, is to be able to take advantage of under the hood optimizations that can occur in order to be able to build that tracking, if you will. But one of the things that is quite useful from a digital twin point of view is not so much a real-time chasing of the data that's coming in, but rather to ensure that this model that has been developed is consistent with previous data, so back testing, as that's called. And then to be able to use things like machine learning or system identification to extrapolate the future or to provide forecasts. And there, of course, your observation is quite true, that you want to ensure that your prediction, perhaps if you really want a faster prediction, then you want to have the system be faster. But then that may imply that rather than have the partial state update be faster, it may be that the machine learning algorithm that is attempting to find the best extrapolation forward needs to be faster. So I agree that there are optimizations that are there, but naively at this stage, there may be more scope for that occurring under the hood at the language level than from optimizing a parallel solution within the partial state updates.
Thank you.
Sure. So in the end, you end up with a sequence for t, t+1, t+2 that are bundles, if you will, of the partial state updates. So each of these vertical pink rectangles represents a single time step, and each of the next time steps may themselves be time or event-based, depending on how the arrival of or the expected arrival of information is from one state to the next. Okay, and just to give you an idea of how that state transition would occur, this is essentially the same as those rectangles now turned on its side 90 degrees, where we have the top column. You've seen this before, but just to bring it back to what we're now looking at, the state variables in the first row, then we have the policies as to how those state variables interact with the state update logic or actions that then influence the state update logic, which is that updating function in green, and then the resulting changes on the sides of the two markets here. Here we have actually a comparison between both the Hydra side of things and the Uniswap side of things. The code that you currently have access to only has the Hydra side activated, but there is a way to compare different buildings of pairwise comparisons between assets between the two types of AMMs. And that's all done within the same CatCat model. Okay, just to give you sort of a bird's eye view, again, for those of you who have been playing with CatCat until now, you've already seen this before, but it's just a way to kind of fix an idea of the framework that you will see across many different CatCat models, so that there's a familiarity with its organizational structure. On the right-hand side, you see kind of a schematic of a large AMM environment. And if you look at the entire system that is outlined there in pale yellow, including events at the top, you end up with the root directory of the actual code, the Hydra, in this case, the HydraDX simulations, the model of which is a subset of the execution notebook at the very bottom there, starting with V2. If you move down a level and you move the events out of the loop and keep in the inner rectangle, you end up with the interior of the model. That's the part that's being executed as a result of how the system is being configured. And so that's one part, that's sort of the outer part, let's say, of the system that drives the system's generation of the partial state updates. So you see there is a function there, which we'll get to in a moment, called partial state update block. So this is where you code those individual blocks. And this feature, which we'll be looking at in a moment later on, allows CatCat to then divide each of these simulation time steps into these substeps where you get the state variables being able to be permuted. So every single one of these slides will have a link for you to the actual folder that you have already presumably installed HydraDX simulations. The state variables file here is to define the global and local states of the system. And remember that what we're looking at here for this distinction between global and local, it is a bit in the eye of the beholder. We typically would think of global states as things that are being conditioned upon by others, and then things that individuals themselves have as attributes or qualities, we would say that they are local. For example, agent states or local states, they would have the holdings of their own assets. That would be a local state of the system. still needs to be updated with every time step, whereas a global state might be the total quantities of assets within the system. And the state variables folder not only defines those variables, but also defines the associated data structure and then their initial state as well. What is the state of the system when the system starts?
I have a quick question.
Sure.
Where do agents fit in, or what is the definition exactly of agents? Is it a state, or is it a set of actions, or how does that fit into the diagram, maybe from the 2 slides back?
Yeah, so go back here.
Or 3, maybe a little further. Yeah.
Here. Yeah. So what's occurring in this environment is the modeling. If you remember back from the GDS, we were looking at systems under which the things that people are allowed to do, the admissible action set, or a decision-making entity is allowed to take a decision inside a particular set. And the design question was, okay, how do we build that set such that certain properties are preserved, or that we understand how certain properties change on the basis of how individuals interact with what we've designed as the admissible set. In that context, anything which is occurring internal to the system, which is taking the state of the system as given, and then making a decision from the admissible action set, would be termed in this context as an agent. And that's this pink diamond in the policies row. So we see that the action in this particular context is building the things that users would be doing when interacting with the Hydra AMM. They may be transferring or removing liquidity, adding liquidity, or swapping into the system, for example. And so this is the way in which there is let's say, a semantic barrier that we're using or leveraging in order to say that there exists a decision-making entity that may be automated, but may also be a human interacting with the system, and that they take actions drawn from an admissible action set. And that's to be contrasted with things that are coming from completely outside of the system that are themselves not necessarily able to interact with the system in a limited fashion, nor is it necessarily conditioning on things within the system that can be designed, but must be simply taken as given. And those are the external effects. Does that help with the contrast? Yeah.
Yeah,
and just great. And just to point out, just to reinforce kind of your question from before, because I think it's a good place to make that distinction once more, that the state of the system, what we call the state, in the GDS framework, that was really nice. We just said that the state is X. And then you saw last week, well, no, the state's not X. They're actually local and global representations of the state. This is one situation in which the decision-making entity may themselves have information that is local to them. For example, somebody interacting with the Hydra AMM may have their own balances of tokens. That's for them, they are local states, and they are allowed the condition upon that. But the locality is simply because they are attributable to a decision-making entity.
Cool. And Paulina, I see your hand's raised. Did you want to jump in?
Yes, I have another question in that topic.
Sure.
So could you give an example for what determines which action is being taken in the admissible action set, or like what governs which action is being taken? I'm picturing it as like a preference guide, or like a guide for, yeah, I don't know. What exactly is it in the digital twin that determines it in like a particular time step, for example?
So if you remember, we'll harken back to the GDS framework just to be able to clarify the distinction between the admissible action set and then the choice that's made, because that is a very important distinction to make. So it's good to bring that up. The way we describe that in notation in the GDS framework, the decision that is taken conditional upon the admissible action set and conditional upon internal and external states, or internal states and external factors, was a function that we called G. And that G function summarizes an assumption about the user's behavior on when presented with a menu of options that we've designed, which one do they take? And that kind of programming of behavior. So using that term sort of in a double meaning. One, of course, you code that perhaps as a module, but you're also assuming that a particular behavior will be taking place, is a way in which you can test alternative modes of behavior that you think are impacting your system. So for example, you might have individuals that you believe are arbitrageurs, so that they're actually looking at an external signal that is coming into the system, and they are making a decision on whether or not to buy or sell tokens or swap tokens on the basis of the difference in the price that is coming from the outside versus what they're computing as the price on the inside of the AMM. That kind of an assumption is an assumption about behavior. It's not something that you would say necessarily is the behavior we always expect to see. The fallacy with that is that you are, number one, unable to even consider alternative behaviors for individuals who may be using the AMM for reasons quite other than arbitrage. And number two, it fails to take into consideration the fact that people look at the system that they are interacting with and then make decisions on whether or not to choose one or more actions within the admissible set. And the simplest way to think about that would be an extreme case where somebody looks at the system and says, you know, I'm just not going to interact with that system. I'm going to take my toys and go home. And then they just simply leave. And part of the admissible action set is not to participate, not to actually interact with the system. So if you forget that part and you say, oh, an arbitrageur is always going to be interacting, there's always this one particular G function, well, then you're going to be very surprised if people suddenly don't show up to your system. So what's going on here? I assume that they were here. So there is this, I would say, tension a little bit. The thing that you can control is the admissible action set. What individuals do with that information is up to them. And so you can build ever more sophisticated models that you hope are encapsulating the kind of interactions you are expecting to see from individuals using the system. But you cannot guarantee that. And so part of the power of CADCAT is to be able to slide in different modules, test the outcomes that are coming from that particular kind of assumption, and look at the real data and see whether or not there's a closeness on the observed values that are coming from both the digital twin and the real world. And if they are matching well, then you could make an argument to say the assumption of that particular G function, that seems to be one which is being reinforced from the real world.
Okay, thank you. And so is then one of the goals of the modeling also to modify this G function and model more extreme behavior in order to test the digital twin?
It's both a goal, but it's also a way in which you can assess the mechanism or class of mechanisms that you've selected. Because one of the things that you can program in, of course, is not just a single behavior, but a whole subpopulation of behaviors. So you can have a distribution of different types of behaviors with different weights, for example. That would say, well, perhaps we have a lot of what we might call noise traders. There are people who are trading for liquidity purposes that we don't know. We just know that it's drawn from some random distribution. On the other side, we may have traders that are informed, and therefore they're taking a price signal and then performing some kind of arbitrage. And we say that, well, we think maybe 20% of the population is behaving in that fashion. So CatCat would allow you to build a subpopulation of the behaviors, so different Gs on the basis of different individuals that are so modeled, and then assess whether or not there's a goodness of fit.
Oh, thank you.
Sure. Okay.
And yeah, Kirti, did you just want to add a last point or?
No, just a quick question. I said, what's the best way to visualize various actions in time steps? Because in most cases, the way I see is AMM is a subset of a larger system, perhaps, like when it comes to managing specific type of assets in my case. So how do you represent these events in the best form, perhaps? I don't know.
It's a question of the view that you find most useful for the analysis or the assessment that you're attempting to perform. For example, one view would be to plot the movement of the global states variables. So looking at the quantities of assets And then computing, as we learned from last week from the math spec, stateful metrics such as the price from that. On the other hand, you may say, look, I really care about these individuals, right? From the previous question, saying, hey, we've got these different G functions. Let me actually select only those agents that have this particular subpopulation behavior and watch how their balances rose or fell. Watch what impermanent loss they had versus another subpopulation. This would be another way that CatCat can allow you to select a particular view of what has happened over time.
Okay. That's useful. Thank you.
Sure. Good questions, as always. Okay, so I think we've moved over to the system parameterization. This is an important component of CADCAD that I wanted to highlight just because it allows system parameters to be used as the core of experiments, the kernel of the experiments themselves. For example, just as a listing of things that may be tested within the HydraAMM, there is a mechanism parameter that you've run across now a few times called A, which is something that's coming out of some of the invariants for the behavior of the system under swaps and other things that can be tested and moved, and it's being defined within the system parameters, this sysparams file. The order of actions, whether people are adding and removing liquidity or swapping, can be set at this point. Size of the trade that occurs for each of the types of trades that are under scrutiny can be set here, in addition to the direction of the trade, which assets are being traded for which. Each of these are things that you are looking at a battery of tests, or in fact, sort of a test grid that you would select, a multi-dimensional grid of combinations of these different types and orders and parameters, and then assessing system goals on the basis of this. This is really where the parameter selection process comes into play, and we're going to discuss this in more depth next week. If you want to be able to build out how many experiments you run for a particular class or parameterization of a class of mechanisms, the config file, .py file is the place to do that. You set the number there of Monte Carlo runs, the number of time steps in total for the simulation, and the simulation parameters. Note that the number of partial state update blocks is the number of substeps within the time step. We're looking at that carving out of those, but the number of time steps is what you'll be setting at the global level of the config file. It does reference the partial state update block and the initial states to initialize the entire experiment, and creates a configuration object that is used to eventually run the system. If you have different constants for setting the number of simulation time steps, the number of Monte Carlo runs, and that's also used in sim setup. This is sometimes present in some models, and more reduced form models. It's coded into the previous file into config file. Config wrapper you see is inside your particular distribution of the HydraDX simulations. This allows the ability to pass an entire CADCAD model as an argument and update its configuration. This is nice because you can build different CADCAD worlds according to the initial conditions. Otherwise, the initial conditions are set as fixed before you start generating experiments over different parameters. Now, this isn't always needed. This isn't needed, for example, when the only things that you're examining are the system parameters in sysparams, but it provides functionality with an added degree of complexity, which is why it's not included in every CADCAD implementation, to be able to vary over the initial conditions of the system. And finally, once you've actually configured the system to run, when you have a single environment where sysparams is defining the experiments that you're running, so that you have a single set of initial conditions, then run is used to execute the simulation. Creates a pandas data frame, and then there's an option to be able to do some post-processing to pull out of other technical information or logging, essentially, information about the CatCat simulation, the desired simulation output into a data frame. You can also, if you wish, keep everything aggregated at the time step, t plus 1, t plus 2, without looking at the individual substeps, but the substeps are, of course, part of the output. So you can also look at how the substeps are moving if you wish. And finally, just like config wrapper was to config, so too is run wrapper to run. this is a way to be able to take each of those models that was created by config wrapper and allow experiments to be run over these multiple initializations of the system. So this is facilitated just as the run.py. It has a run method within it, but it allows you to be able to execute these simulations across multiple configurations. We haven't been using it for the simple notebook that you have examined, but for larger systems where you are examining, well, what if we initialized the pool in an AMM with different token balances? Well, those initializations themselves can be facilitated by using this config wrapper and run wrapper workflow. And finally, we have inside this outer part of the model-based directory structure, the plot utils.
I lost Jamshid's audio. Does anybody else still hear him?
No.
No,
Yeah, there's no audio.
I can just jump in.
Okay. Oh yeah. All right, Barlin. Yeah, go for it.
Sure, I'll go for it. Yeah, since I wrote all this anyway. Yeah, so yeah, there's the plot utils function. So essentially just add plot functions here that we can call when we're doing our analysis. They are some parts generic, but then some have been made like specifically for this model in terms of like pulling in certain sets, like specifically certain sets of the to do the Hydra agents to essentially get a view into the local state. And so like you'll see some of those as well. But you know, so any or all can be used and can be customized as needed. If Jamshid, if you're totally, I just can't share screen, so I don't know if there's a way to override that.
Yeah, you should be able to. Well, I wonder what happened to him. But yeah, we could. Is this the point where you guys would have switched anyway?
Yeah, I could have jumped in at any
Okay.
point around, so it's totally fine.
Okay. Then yeah, let me see if I can.
Yeah. Wow. I'll
somehow.
Close. Yeah, he was almost there.
Or maybe if you are you able to share screen? Right
no,
now?
I don't have, because while you cannot start share screen while other participant is sharing.
Okay, there we go. Can stop him.
Okay.
And now you should be good to go.
Hi, since Jamshid was in the next room anyway, I managed to get him into my room and he will be able to continue.
Oh, okay.
Okay.
That's fine if I think it's fine, Jamshid, if you, unless you, I can drive.
Yeah, I don't have any. If you do, you want to continue, or do you want me to continue? I'm happy either way. I apologize, everybody, for the.
That's fine. I finished the kind of the plot details, and
Yeah.
then yeah. So then as here, I mean, we've essentially dug under this heading before, but we can look again to essentially say that all the in that parts directory is where we contain the files. Essentially,
Barlin, would you be able to share your screen?
Oh, I'm not sharing?
I don't see it unless someone else does.
No.
No?
No.
Oh, no, I keep it's telling me I am screen sharing.
I'm going to see if I can maybe quit out of mine. Mine might be holding the focus here. Hang on a second.
Maybe I was already in full screen mode. Let me try.
Yeah, maybe try just re-sharing.
Yeah.
But I did stop Jamshid's screen share, and he's no longer in the meeting, so I don't think that should be an issue. Sorry about this, everyone.
Yeah.
Oh, yep, there it goes.
Now, yeah. Yeah, I was already, I think it was just like already in full screen mode, and then it didn't like that, so I had to leave. Okay. Yeah, so basically we have a set of files under parts. There's no a special like exact template for how we do that, how we separate these files. We try to make those logical references. In some cases, if we have a model that has multiple partial state update blocks, then we might do that as our delineation between the different parts. In some cases, there might just be logical groupings. And in this case, we do have kind of this higher order structure here, where essentially the Hydra V2 Hydra is kind of serves as the director of traffic. And so essentially what we have is that in action list.py is where we're essentially prescribing the sets of actions, or in this case, we are prescribing those sets of actions. In other cases, that list that you could change the logic to make that not prescribed. But either way, you could use the logic that is there to essentially set forth the actions to be resolved. And then the V2 Hydra kind of serves as the director of the traffic, taking in those actions and then sending them out to each state variable to essentially to be updated and resolved. And so the different parts here are essentially doing that there's some in the utils and mechanisms. The coefficients are those like the C and the Y, resolving agents. And then because of how we're doing the other half of the AMM as that set of reserve assets, that's a class. And so then we have essentially like that's why they have asset utils for essentially the class methods that are also kind of like doing some of the resolving. And then you'll also see here that we're not invoking it in this case, but we do have essentially the Uniswap mechanisms as well that could be turned on to be tested as kind of an A/B test scenario, and actually in parallel, I should say. And then so then essentially what we have in that action list there is the availability to have these actions, essentially the swapping of whether risk assets or swapping with HDX or adding or removing liquidity, and have those essentially be set forth and set this system in motion, set the dynamics of the system going. And so those are, and then we see in those parts before about how the local state as well as the global states are updated. Okay, so what I want to, so I'll stop there. Is that a check in with Jamshid to make sure that's okay? And
yeah,
then,
no, that was totally good. Thanks. Appreciate
and then
that.
as well as check for questions if there's any. And I'll be hopping over. So I have a series of slides here, kind of like showing through the output, but I think I'll just hop over to the code so we can kind of just see what these things are, but you'll still have the slides for reference.
Gene, did you want to jump in with a question before we go to the code?
Sure. I mean, I was just wondering if that parallel between Uniswap and this implementation can also be observed through the substep idea.
Yes. So yeah. So essentially, how we did it, if we kind of look back here, what we really established, and actually probably this one a little bit bigger, so we can see. So because we essentially established two states, right? Like essentially a Uniswap state with its local agents and the Hydra state as it's with its local agents. But what we did at some different stages of testing were that we could say that because we're in this kind of like prescribed set of actions, we're taking these actions independent of which state you were interacting with. We could say, okay, I just want to swap, X for Y. We could take those actions and resolve each independently. And how we did that was because one of the things to note here is that you also have control, like a note about partial state update blocks, is that you have the availability of having the entire state available to you to both be referenced to make a decision, but also you have the control about what or which of the state, which subset of the state actually gets resolved or updated at each block. And so therefore we were able to use this logic to essentially say, okay, like in this first block, we'll take in an action and resolve what happens in Uniswap. And then in the next block, in the next partial state update block, we would take in the same action and resolve what would happen in the Hydra world, and essentially say that in the Hydra AMM, and say that, okay, like those two blocks would make up the time step, and therefore then we would have this parallel where we would say, okay, at time step 17, we saw this action come in to both of these, and here was the resolution, and do that comparison. So yeah, so that's
really cool.
Yeah.
Thank you.
You're welcome. Any other questions? Okay, so then
I have a question.
Mm-hmm.
This is actually going back to what Jamshed had said. If the whole thing is sequential like this, and if you are actually breaking up what should be parallel into sequential, is it not vulnerable to, say, front running by high frequency traders in the Hydra setup? There's a lag. There'll be an inbuilt lag in the response type, say, in comparison to, say, some other exchange.
Yeah, so yeah, this is something that we've dealt with as well. So you can think of it, so if you're looking at, say, a block, right? It sounds like you're looking at a block of transactions or a proposed block of transactions, right? And what you're saying is, and we can, like, that's not what this model was necessarily built for, but it's still flexible enough that it could be leveraged without too much overhead in that way. But you could take in, essentially have a set of possible transactions, right? And if you're looking at, say, front running problems, then what you're saying is that, okay, there will be an actor that comes in and changes the order of that set of actions, right? Or imposes something in the beginning, and so that can be done with this as well. Like you could essentially have like a partial state update block coming back here. You could essentially have, okay, here's a possible front runner policy that sometimes gets triggered, right? And what it could do, it could be triggered here as first, but it could be looking at, essentially, say, the set of proposed transactions that have come in since the last block, which would be like essentially like your last time step, or if like, say, like it was put in, say, like this is, you could put your front running policy here in the second and say, okay, here are all without doing resolution, right, like of the state, you could say, okay, like here are all the transactions coming in from all the possible users, and like essentially you would have, like, say, like a mempool state here, where it's essentially recording all of the possible transactions essentially queued up, right, but have not been resolved. And then you could have a front running policy that comes in here that can manipulate that mempool state by putting in a transaction first, right? And then you could have the resolution of that mempool later within that block. Does that make sense?
Not at the moment, but I mean, I'll go through it later and then I'll revert.
Okay. Okay. So yeah, so we'll start looking at like what is in the model and what the output looks like, very specifically to the model, but as well as some what also kind of comes packaged when you run a CADCAD simulation. And so I'll jump over so you can kind of see it from here. So I'll just jump over here. So like I said, you'll have, can you guys see VS Code?
Yep.
Okay.
Yep, can see it.
All right. So yeah, so what I want to show you, like I said, you'll have the slides for reference. So you can kind of go through like how I broke it down a little bit, tried to break it down some for you guys. So when you run CADCAD, so these are actually, it's always bothered me, it's been there forever. So we have kind of standard data science libraries that we import for like pandas and NumPy or plotting. So those aren't required for essentially in running a pure CADCAD run. We kind of standard typically output a pandas data frame, so you kind of want that. And then essentially what we're doing is calling this run function here, and that run function has already then reading in a config, so the config.py has already essentially made the config object and set it up to be executed. And so the run function is doing the execution of CADCAD. So what you'll see here, like typically when you're running kind of any CADCAD model, you'll see this kind of just this output here, where you'll get a kind of a readout that you're executing and what the simulation you're doing is. So time steps, we just happen to choose 100 time steps for this. We can change that. Params, that's giving you just the total number of parameters that are in that essentially in that params dictionary. So that like the number of key values of keys. So in this case it's 15, but that doesn't mean we're not doing like a set of 15 of a parameter suite of 15. That's just telling you that. In this case is one run, and I'll show you how that changes. And then vars, that's again similar to the params. That's the number of state variables that we have, and that can be like pared down quite a bit if we're not doing the Uniswap version, and we'll take a look at that. And then so we essentially have, because we're doing the simple one, we're essentially having these are all Python counting and starting at 0. So like really these are just essentially saying one of each of these for both the sim and the subset, and we'll talk about what those are as well. And then we typically might, within the model, if we're debugging, we're interested in printing out data. So these are like any or all set of print statements that you've kind of put within your model to kind of check or kind of observe would occur next, and sometimes depending on how you set up your environment, it could be here or it could be essentially in a different screen. And then you get the total execution time. So let's talk about kind of some of these, and it'll be easier to talk about by looking at them. And so this is the actual output, and just like a subset of the output. And I kind of took the, like I said, the CADCAD side of the output. So The other section of the output will be all the state variables that you've named. But here is what you're getting from CADCAD. And so what you start is with the 0, and you see this 1 time step 0. So that's what we call our genesis state, or the initial state of the system. So that is not an execution through those partial state update blocks. It is the set of values that you've started the initial state with. So that's our first record is going to be that, just that. So time step 0, sub step 0. This is just our first run. I'll talk about the others in next. And so then what we see is, then if we focus on substep, in this case, we have 3 substeps. So that's why you'll see this 1, 2, 3 going on 100 times after that, because we have 100 time steps. So you can see how we have the 3 1s for the 3 time steps and the 3 2s and so on and so forth. Now, what we'll see if we had Monte Carlo, and we do have a stochastic vector, so we can set up Monte Carlo runs, and then we would see that this number would be reflected in the Monte Carlo runs. So if I wanted to say change this to 2, this will run. Some of the plots would bark at me, but so just a couple of things here to note. Also, if you're running, depending on your environment, you always do have to restart your kernel, because kind of the Python memory management will it tries to streamline things. And so if you had a change to your config object that you've made a change in your model somewhere, and even if you save those changes, if it essentially doesn't get a trigger that this is a new config object, it'll actually execute on the previous config object. So you really do want to make sure you restart. And the other thing, like in this environment, I like to clear my outputs, because if say I'm way down looking at a plot or with some output value, if I don't clear my outputs, sometimes like there could be an error that actually occurs, say in the execution, and the error would sit there, and but I'm say like looking down here and trying to see some output and make sure it's right, and that'll just like in this environment, it'll just re-output the previous output even though it didn't run. So that's why I do that, and then just run all, and this should work. And now we'll see. So I made that. So now I see 2 runs here. Right, and now I can see like now all these lists have 2 entries. But you see the only thing I've changed is to have we way back when we call that N for a Monte Carlo run, so that's still here. And so if I'm looking at the head, I don't see a change, right? But if I kind of just take this and take this, then what I'll see is I'll see run 2, and I'll also see like time step 1. Yeah, I'll see the ends of the time steps here. But you can see that this is run 2. And yeah, we're getting to the end. And so we would have essentially double the amount of output. So let's see, so it's time steps, substeps, runs. So if we had subsets, and we have done some of these for this model where that is where we would get into, say, if we were doing a parameter sweep, then we would see subsets. And so in this case, we don't have a parameter sweep set up. I can see, I haven't tested this, but let's just, well, like this won't change anything. So even if I actually, this would just change some of the actions. So which should be fine. So if I did something like this, then I would now I should now see. Now I see that essentially now that I have 2 runs and 2 parameter values, now we see, okay, like, you know, it's kind of that almost like when you're counting in binary, right? Like we now have, so we're now up to, like, you know, a nibble. And so, yeah, so we see like 0, 1, 0, 1 for the runs, and now we have 2 subsets. This like 0, this the first subset would be that with the parameter value of, in this case, mu of 1,000, and the second one would be with 900. And we would see that also, we see that reflected here in the tail, that we're now also on subset 1, but if you notice, like we're at 1,200. So if we like kind of looked at, let's see, but yeah, so we would see that, I think it'd be pedantic, but yeah, if we like kind of looked around 600, we would see the shift over from like run 2 subset 0 to run 1 subset 1. If we can follow all the Python counting versus human counting and the mix of those things. Yeah. Is that, and then the last thing would be simulation. And in this case, we see that simulation matches the subset, but there's essentially one higher level where we can actually bring in, say, other models, other system models as part of an overall experiment. So we call that entire thing an experiment. And so therefore we can actually get a unique simulation tag over say bringing in another model. So essentially having, say, like 2 models or multiple models and bringing them, creating the configs associated with those models and executing that entire experiment. So that's also another way where like we might talk about like parallel worlds, and that's kind of a there's a pretty recent, as in like last week, release of CatCat. So that kind of employs that that extra order or level over that more. So any questions about that, kind of how we're seeing the partial state update block and how that looks in terms of our records? Yeah, there's a question.
Yeah.
Go ahead.
Can I ask?
Yeah, go ahead.
Go for it.
Yeah. Okay, this is I wanted to know, see, the policy of invariance for HydraDX is still not quite clear to us up till now, because HydraDX has got a unique invariant policy. And the second thing which I'd like, it's quite a daring proposition which I'd like to make. What I say is that supposing we find a bug in this concept, say if we point out that it's feasible to do front running, not just HydraDX, but for the whole AMM concept. Do you have anything, I mean, like, if you research it in those ways?
You're breaking up a little bit on the second part, so this.
Okay, I'll explain as in principle as to why it may be feasible. In the sense that prices revolve around a certain point. Based on the invariant policy. So because if there is an inbuilt lag, then it becomes easy to use high frequency trading to bracket up and down. Is there any reason as to why in the HydraDX proposition, it will not be vulnerable. Because I have implemented algo trading, high frequency trading systems. And I have my colleagues in JP Morgan whose only work is to actually define extremely high speed systems.
So are you, so one of the first things, this I think is a little bit off topic. Like I do want to make sure that we get people, but in terms of like firm running, are you presupposing that this is Ethereum and that that transaction ordering can be manipulated through transaction fees?
Not saying that the transaction can be manipulated. I'm saying that it can be front run.
Mm-hmm.
There's a difference between manipulation and actually see. I mean, it's like, you know, impermanent laws or arbitrage should be more accurate. It's a form of arbitrage.
Mm-hmm.
Currently, almost all transactions on blockchain can be front run. We haven't seen like complete solution yet to this problem, but we have one mechanism that is a little bit making it less of a problem, but it still is a problem in all, like a lot, or maybe all or most of the blockchains currently, not the private ones. But yeah, it's kind of off topic. I'm happy to talk about it, but I'm not sure if right now. So it's up to you, Barney, probably.
No, actually, I'll kind of resolve it. It's probably an unfair question because all tradable propositions can be arbitraged away the other way, so that it doesn't exist. But it cannot be arbitraged away in the high frequency area. So in that sense, my question was unfair, and it's not a problem which can be tackled the way you just explained, Jacob. So in that sense, my question was unfair. But the reason why I made this particular statement was because my hunch is that there may be a bigger opportunity in AMMs because the opportunity may be bigger. That's right.
Yes, maybe that's plausible. I think so, because you know the system and you see the inside of the system. But that's also the thing that you don't see the other systems, and you don't know what's happening in them. Only some people do. So that's like a counter argument to this. But yes, I think it can be partly solved. Maybe even completely, but that takes like a whole new whole new engineering problem than we are right now solving. But yes, this is a problem in, I think, like most or all of the blockchains currently.
Not just all blockchains, all trading.
Yes.
Yeah, this could be a topic that, I mean, I think it's come up already once or twice, but we could also discuss it more in Discord or in one of the share sessions. But yeah, I think it's obviously an important question for blockchain.
Yeah. No, yeah, and Joseph is right too. I mean, I have seen some of the I've attended some lectures about essentially the high speed connections from NASDAQ, from like the in New Jersey, and getting the NASDAQ feeds, and essentially how that can be, how plugging into those can yield tremendous value, and a proximity to those. So yeah, so you're right, Joseph, about that.
Yeah. Could you answer my first question about invariant? I mean, what is the invariant formula in HydraDX?
Yes.
Will it
Okay,
be
so
explained later?
yes, we have, I think the one that is currently in the program, that is like one of the first ones. From those, we saw some problems in the system that can be resolved differently. So we were, like Colin was searching for more with different set of requirements. And so you will see the first one and maybe even the second one and third one. And hopefully once we settle on the fourth one that is currently looking like is the final one for at least for version 1, we will definitely share it with you. So the answer is,
so we do have a fix, and I think Barlin's showing it here, or pointing, or it's somewhere in the code will be a fixed invariant formula for the purpose of this course, kind of for the purpose of showing CADCAD. And so maybe we can, Barlin, I don't know how you want to incorporate that, but maybe showing sort of what that invariant formula is.
Yeah, so I did go quickly over that last, I mean, I and by quickly, I mean way too quickly breezed over those formulas. Did we, hang on, I'm just gonna look and see.
And we'll just give a 25-minute time heads up.
Yeah.
But I think we're doing good so far. Your call.
Yeah. Do you want me to bring up the last lecture and go to those slides? Because I know we ran out of time on those previously.
Yeah, well, we should make sure to finish this topic today.
Okay,
if we have time to do a tangent now, for sure, or we can wait till the end and jump back over. I think all up to you.
Yeah, I think we'll wait. I think there's I think we'll wait because we're kind of in the middle. So
cool. I'll add a note though and make sure we can come back to the topic.
Yeah. Okay. And so the last thing on kind of this set of data that I want you to see is something that we often do is, because you get a record at every substep, and that may or may not be of your interest. It typically is if you're setting up the model, but if you're, say, exploring or say looking at a bird's eye view and looking at some results or KPIs, etc., then you may be less interested at seeing each of these substeps. Some people may be very interested in seeing those substeps. So like one of the things that you might typically see is, like, this is kind of bad code roughly, but kind of just to show, I could just rename it, but just to show what you might see that might like kind of throw people off for a second is, so what we sometimes in this kind of post-processing method, all it's really doing is actually just taking the last substep and saying like, okay, that's the same as the time step, like it's the same record, so we're just essentially filtering out all the substep 1s and 2s. So now we see just substep 3. So it just clears the water sometimes if we're looking at say like a large set of data. So that's just to be aware that you might see like, some plots where, say, like if you just plot against the index, you'd only see like kind of every 3 in this case, and in other models you might see more, but so you can see how the index here is every 3 now. So I want you to be aware of that as well. Okay, so then let's look at the actual data. That was all just CADCAD kind of binary multiplication, but so what we have here is really the set of state variables for the Hydra AMM, for the OMNIPool AMM. And so what we have is we have pool, which is actually a class of of all the reserve, what we call it, kind of the risk assets. So like, and in this case, what we have is like I, J, and K as our three risk assets, and each one of those has its associated set of the state variables that we had defined as that kind of that vector. So like, so we have the amount of the token, so the RI, the R, like, so the R, sorry, for each IJK, we have the R. We have their share, the number of shares associated with that, so S. And actually I can just kind of show you here, like, and you would find those here again, because this is the class, so this is like, so we have R, we have S initialized as the same as the reserve for the value, but then that changes. Then we have the coefficients, so essentially one of the, like, essentially the, we sometimes, yeah, so we have coefficients, sometimes we use those, just be aware, like, sometimes even like that earlier discussion about like invariance, that we have some invariance that in general that stay invariant under sets of actions. And I'm not saying that what the coefficient is. And then we have the relative price to Q, so the Hydra AMM value. And then we don't use this anymore, but I just want to be kind of like aware that you can also set bring in other attributes that say you were interested in or looking to define. So in this case, like in one version of designing this that we were looking at, say like the delta price, the change in price. So kind of I use that as a placeholder. So in this state variable, at each one of these records, you have a full set of this information across along with a length of the vector for the number of assets you have. And in this case, like in this model right now, we have 3. So we have 3 of those at each point there. And then, so we have Q, which is the number of Hydra tokens in the OMNIPool. We have H being the record, kind of in this, again, like this is where it's like kind of right now the one-to-one of what's happening in the OMNIPool for the essentially the counting of H of Hydra tokens affected by this OMNIPool, and like it essentially had that there for availability that say other things could affect H, say independently than this. And then we have the shares associated with Q, and then we have Y, which is one of the variables for this OMNIPool itself, and into that. And then as well as C, so C is essentially the coefficient on Q. Again, the risk assets each have their own C vector. And then I jumped over, so then Hydra agents, and in this case, what we've done is we've modeled the Hydra agents as like this is actually a data frame. And I talked a little bit about that earlier, that the data frame essentially is like, it just happened to choose initially that we had essentially 8 like actions at a earlier version of this where we just had to say I and J, and we had like essentially 4 actions of swapping each way and adding and removing, and so like a way to kind of verify each one individually, so you're not bound by that number. It could be changed. You could make it all one super agent, or you could break everything up into many. It's actually and so that's what is actually available at each record, is the resolution of, say, like of this data frame, essentially, like where you would say have the updated values for each one of these agents, and each one of their values for here. So this is going like kind of horizontal and vertical. So if you imagine that, like, you know, there's 8 entries here. So like agent 0 has the kind of the first column of initial values, but you're getting the updated value, each one of those here. Any questions about like so that's the state variables associated, output associated with the time steps. And then lastly, kind of looking at this, well, probably not lastly, but then what we have is kind of like our stochastic vectors or our randomness that we're looking at. So just kind of breaking this up, otherwise, because of the huge wide list gets truncated, so we can kind of see that it what we're doing here is assigning randomness, and so we are tracking this as a state variable. That way it gives us the ability to see what was happening. One of the things with CADCAD, if you have actions, if we kind of think back to kind of the green aggregator and the green diamonds in those substeps, like those are actions, but they don't necessarily get written to the state directly unless you actually choose to make a state variable that essentially tracks that or writes that somewhere. What happens with those actions, like you create any action, what we call like a policy or an action, is created and output as a dictionary always. So like here, we're just returning this action dictionary. But this is not actually part of the record of the state variables unless you make it so. So like the record of the state variables, like that's what you get. You're getting the resolution of the actions. So in this case, what we're doing is we're saying, okay, like what is the pertinent information that we need to essentially track? And in this case, it was all the random things because we were prescribing the other anything else in terms of the actions. But this is the actions that we're taking, and we're essentially being able to track that so that we can do. You'll see next week in the parameter selection how we say, okay, given these stochastic vectors of randomness and given the output, you know, how do we make logical next steps about those two things together, let's say. And then kind of the last thing here on the raw output. So in what you actually have, so like I said, I was selecting some of the fields, but you actually have kind of these. We're not doing anything with these Uniswap state variables, but they're here. But like, and this is where we kind of have this parallel world where we would essentially, like, we had 3 instances of Uniswap, essentially V2 pairs, and then Uniswap agents just trading on each one individually. So we had not set up, say, like in an arbitrage world across those pairs, but we had essentially how those would resolve in these kind of set of 3 instances, compared to what was happening on Hydra. So that is the raw output discussion before we can kind of like look at, say, some plots or go back into what is in the model itself. I'll pause here. Yeah, there's probably some questions. So I'll pause here and also bring up. Are there any questions? And I'll try to bring up the previous slide.
I think it was just Colin mentioning the something about the invariant, adding an equation to help with context,
okay.
but
okay.
Yeah, I think we're good to jump back in.
Okay. Before, so here, let's do this.
Unless there were questions not posted in the chat, feel free to jump in, anyone.
You can.
Yeah, I was asking like if you could have a session on explaining how that particular invariant behaves. It looks pretty complicated.
Yeah, maybe that's, I have the invariant fix topic down as something that we should definitely cover. So maybe we just save the time for the rest of this lecture to finish the slides and then come back to that at the very end if we have time, or we could circle back at the hack and share session on Tuesday.
Okay, so yeah, so like I said, in your slides, you have kind of like roughly what I talked about there. What I did want to touch on is, essentially what you're actually getting, so we kind of looked at it through the scope of a pandas data frame, kind of like the go-to Python place, but like what you're actually getting is essentially this list of dictionaries. That is the actual raw output is actually a list of dictionaries. So like we just very simple to convert that to pandas for our walkthrough, but that's what you actually have is this list of dictionaries. So therefore, you can do whatever you can do with a list of dictionaries, and so there's more that you can do. So we can see that like there's we have pros and cons about like using pandas. Well, like if you know Python and you're working with Python, then you know something about pandas. They can be, so especially it took some work back when we've kind of added these levels of metadata and really like multi-levels. If we kind of think about pandas and how we do like multi-level indexing, essentially by having this kind of multi-level tier about experiments, we had to kind of like do quite a bit to kind of flatten the CADCAD data and make sure that the metadata associated with the simulation was indeed tied correctly to the results output. And a note about that would also include that in this case, if we saw with the simulation output, we saw that this was just, yeah, so I should note, if you noticed before that when we just did one run before, when it was just one value, it did not say parallelized, it said something else. And so there's not a guarantee like that the simulation executions don't actually occur in series, like that it will be parallelized, meaning like the fact like they'll be separated and the fastest one to come back comes in first. So we don't have that guarantee of list order. But we do handle that correctly in how we tie the metadata to the actual to the actual experiment setup. I just want to get to that here. So like essentially, yeah, I told you like some of these plots were just going to break because of what I was playing with. But oh, I think it was before. I just want to show that. Oh no, it's not on this. It's not on this experiment because this was just a one-off experiment. But I'll make sure that that gets in also. This so you can kind of see how we correctly tie in the metadata associated with the experiment to the results that you're getting. So then whoops. Back.
I think with the parallel stuff, it's also nice that in blockchain everything runs in series, and the actions are actually not being performed in parallel. So if you can like simulate set of outside actions and put it into blockchain, then you are simulating the blockchain part, then you can randomize the inputs, but in the blockchain it will always be serial execution.
Yeah, that's a good point.
So you probably need a layer 2 type of solution. A
For
wrapper
scaling,
around,
right?
yeah, for scaling.
Oh,
Otherwise,
yes.
yeah, otherwise it'll be impossible. I mean, I think you're open to one of the, I mean, if you're doing trading, blockchain is not the ideal backend in the current. You will need a layer 2 solution.
Possibly, yes. I think so. I think like blockchains will act as settlement layers. There are some hybrids, but yes, if you want like performance that you have on what you are used to, then most probably you will probably go to some layer 2 solution or some different construction of the blockchain, but it will still need to be serialized in the end. I think to have consensus about the actions. I'm thinking if there is some parallel consensus that is being worked on. I don't know.
It really raises a question as to what is the nature of persons transacting on DEXs, on AMMs. Is it, I mean, how much of it is, in inverted commas, real transactions? And see, real in the sense that, is it just a whole lot, is it a chain of arbitrage? Or is there like, I don't know, because this whole crypto area is so nascent. I don't know whether it's even valid to ask, such a question.
You're asking like what percentage of transactions are arbitrage versus sort of regular trading? Is that what you're asking?
That would be the first level of question.
Yeah, I mean, you can think of it like that. That's a good question, and a question that goes into modeling any design, right? Arbitrage, basically by definition, is how AMMs are going to lose money, right? And so the fact that AMMs, many different AMMs, are not, that the fees are compensating more than adequately for the impermanent loss of the liquidity providers, is a sign that it's not all arbitrage, or either that or it's very bad arbitrage that's not succeeding, right? But yeah, in terms of modeling a new design, right, that's sort of a good question. You have to make an assumption about like what percentage of the trading is just arbitrage to external markets and what percentage is, someone has token A and wants token B. But to me, the fact that existing DEXs and AMMs, make money for liquidity providers is a sign that it's not predominantly arbitrage.
Because I leave it at that because I'm actually learning this whole area, so I don't want to ask any further. But seeds of doubt are there.
Yeah, it's a good question. So yeah, Barlin, we just have a few minutes left. Do you think we're going to be able to get through?
Yes. Yeah, I do. Because essentially, so just finish up here that so another option would be XRA, which is like more tensor-like in structure, which actually can lend itself. Really depends on the model and essentially the data structure that you are essentially you keep in mind, like when you're setting up your state variables, you're actually imposing a data structure. When and even wait the step before, when you're specifying when you're making the mass spec, like that is the realization in when you're writing your state variables, is that you're imposing that data structure that you said exists. And so like there are places where you would use XArray in favor of data for pandas because of the data structure you're looking at, and it does lend itself also with kind of like this hierarchy better if you've dealt with multi-level indexing on pandas, you know. So we've seen that. We've kind of seen this, just another visualization about like kind of what we've been walking through, but kind of want to tease for a little bit about like both a little bit more about what you can do with X-array, but then I wanted to make sure I got to here for kind of like a little bit of tease for next week as well, where essentially like you can, by having this multi-level hierarchy, it does lend itself to say something like, say like a search grid for in a machine learning pipeline, or closer to what Jamshid will be doing with essentially parameter selection under uncertainty. So that, oh yeah, and then can't forget homework, right? So this should be the last slide. Yep. Yeah, so what we're looking at doing is, yeah, both you've had the model, you've looked at it, and hopefully you've gotten progressively more familiar with what's happening in it and what the output looks like. So you can kind of take you know, your system of interest and kind of think about what would go into, again, like, so we're not saying code up a model and have a model running, but more actually the thought about, say, making that CADCAD spec diagram, and you know, and making it a kind of a test plan. Like kind of go through again, like the exercise about that thought process, because that often, you know, like going back to the engineering part about iteration, you know, like we iterate over requirements and mass specs to get a good mass spec, but that doesn't mean the mass spec is done, right? Because like then you're modeling, and even this exercise of saying, okay, like now, because I'm really taking a much different view about, say, like a mass spec, which is like, okay, here's all the stuff, the states and the actions and the mechanisms. All right, what's actually going to happen when these things are set in motion? When you kind of start wiring it together, even like this exercise as a process, something like this can lead itself to say, wait a second, is that right? If this happens and then that happens, does that make sense? Like, do I need to go back and look, say, at the mass spec, or do I need to just test this out and write that down as a possible test in my model of, hey, what if I swapped out these two things? I should check that, say, that corner case, for instance. So yeah, so again, like kind of just that exercise of thinking through how these would start to look as a CADCAD model or as a diagram, I think will kind of lend itself to get you to think about your mass spec in a slightly different light, and ideally give you both an update to your mass spec if there's something you weren't sure about, or highlight experiments that you would know you would need to run in order to test something out. Just, I know the last note on that is, like, there are a lot of times in that preliminary design phase where we've written a mass spec and we've said, you know what, here's a place where we've gotten as far as we can go without doing a series of tests. You know, we know that there's some parameter, it's simple as some parameter value, but it could even be as here's a function with like kind of like a set of candidate functions, say. You know, those sorts of things would be mapped out, and you know, we're not doing using CADCAD models as like a fait accompli, like, okay, it's done, like here it is, I wrote the mass spec, here's the model, done, right? Like it's, hey, there may be things to actually test, again, that the computer aided design part, right, of like, I'm using this to help me make informed decisions about a system that I will deploy.
Just to interject there, in that slide, the highlighted link on CatCat tutorial is actually something that Chris has put together, and we'll distribute the link also into the channel in Discord. I don't know, Chris, if you want to mention just a few words on what you've put together there.
Happy to. So thank you, Jamshid, for the pointer. There is a tutorial, as you can see, and I will be posting it into the channel after the session, along with the link to the repo, because there is a new push with newest version. It includes 2 additional notebooks, and these notebooks you can use for the visualizations of the different experiments, because in the current notebook that you had, you were not able to visualize parameter sweeps accordingly, because there was only all of the runs were executed in a sequentially. So you would see 3 different actions going on in a sequence, instead of having them visualized on top of each other. So there are additional notebooks that you can explore, just to see how, on the one hand, CatCat would produce a data frame and where the different results are located there, and then on the other hand, also to see how different plot functions would make you visualize these plots accordingly. But this is only one exercise. So the tutorial actually consists of 3 different parts. The first part is just an explanation of the model structure. So you can see things that Jamshid and Martin have been discussing today. So you really can see which files are and what you can do with those files, so which changes you can do there. And then in the second part, there are some exercises to do, or more rather, I would say some things to try. So I wanted to phrase the tutorial from your perspective. So what you would like to do if you were, for example, to assign different starting conditions for the agents. So different endowments of their initial token states. And there is, for each of such things, as for example, initial endowments or different parameter values, there are different exercises for you just to step them through. You will see where to do it in the code. And then if you execute, you will also see how these changes manifest into the simulation output. So I think if you just do it step by step, and feel free to ask me questions in the channel if you feel that you get stuck somewhere. But I think that if you just do it step by step, you will familiarize yourself with the structure, but also familiarize yourself with where to apply changes such that particular effects to the model execution happen. And yeah, this could be a good introduction into how to structure your experiments. So I hope it is. I hope this helps.
Well, yeah, I think parameter selection is a really interesting topic. Obviously, that's what we're going to do tomorrow or next week. So try and break the model this weekend. Very cool. Are there any templates or frameworks that would be helpful for this homework assignment? I know we've seen the flow of the state update function, the policies, and then kind of these templates with the diagrams. Is that something that would be helpful for this homework session? Or is it more focused on the initial parameters and
it's more parameters? It's more about kind of figuring out where would you put your system of interest into the way in which the CatCat implementation is structured. And so the tutorial kind of breaks that down again in the same way that I had broken it down originally, and as Brian has gone through in detail. So it's more about that and less about operationalizing alternative parameter specifications or alternative mechanisms. People are free to do so naturally, but it is really about trying to figure out exactly how in this workflow you would then be able to create something that is amenable to a computer simulation. And then we'll take up the idea of how to specify and test against mechanisms next week.
Cool. Perfect. All right. Then does that cover everything from your end, Barlin and Jamshid?
Yep.
Awesome. Yeah, well then, thanks for the presentation. That wraps up today's session. I think I'll probably be in touch on Discord, and see you all next Tuesday.
Oh,
great.
Okay, bye guys.
Bye. Ciao.
Thanks. Bye.